Okay, sir.
Okay, today's lab is layout design of a NAND gate and an OR gate. To manually check the mask layout of a NAND gate and NOR gate, objective to check the design for design rule error, to check the functionality of the design using simulation with the built-in simulator. So basically, আমরা আমাদের গত lab, that means in our previous lab, we have seen the mask layout of inverter. Now you will be seeing the mask layout of NAND gate and NOR gate. Okay, so this is our this is our NAND gate, and the output is A into B bar. And at first, what we have to do, we have to let's see the truth table first. 0 0 1 0 1 1 1 0 1 and 1 1 is 0. So let's convert these into our switch level. That means simplified transistor level diagram. This is the NAND gate 2 2 2 2. Okay, obviously here 2 2 means we use 2:1. That's why 2 2 2 2. Okay. So 2:1 means since you have one path and one transistor in one path, so 2. You have another transistor in this path, so you have 2. But you have 2 transistors in this path, so you have 1 into 2 and 2. Okay, so this is the sizing. Since this is the sizing, so let's go to the mask layout. Okay, before going to this mask layout, I want you to see these. Then we will go to the mask layout. Here you can see this is the source, this is the source, this is the drain. This is the drain actually. This is the drain. This is gate. Then this is drain. This is source. This is drain. This is source, right?
This
Okay.
one gate.
This is gate.
This is gate.
Gate. So what you have to understand, see the PMOS, their sources are connected and VDD is connected. PMOS, their drain is connected
Yes, sir.
and their drain is connected to the NMOS drain, right?
Yes, sir.
That A has a source, that source is connected to B's drain. And the ground is connected to B's source. So this information will be required when we will be doing our lab. Okay, let's go and open the software. This is the software. First, we have to change the foundry. Remember, select foundry, 90 nano, and we have to make it 1 lambda. It is already in 1 lambda, so we are good to go.
Okay,
So
sir. স্যার এখানে আমি ভুলে গেছি স্যার, এটা যে 90 ন্যানোমিটার, এটা স্যার সিলেক্ট করলাম কেন?
So this is for the sizing. All the sizing,
Yes,
all
sir,
the
yes.
sizing that was calculated for 90.
90. Yes, sir.
Now we need P MOSFET first. So P diffusion. So I will take 14. 1 2 3 2 3 4 14. Here you will have 12.
14 by
So
12. Okay.
here you have 14. Here you have 12.
12. Okay.
Okay. Then you need N. See the sizing. Here for A, your sizing is not A. For A, your sizing is 2.
2.
And for A, your NMOS sizing is also 2. Since they are equal, so if A is 12 lambda, that is for PMOS, NMOS will be also 12 lambda. Because both of the sizings are same, because 2 2. So this will be N. Understand? So they will be same. So what I'm going to do, I'm going to give a gap. I'm going to give a gap of 12 at least. This is 8, 10, 11, 12. Okay, this is 12. So this is in between at least 12.
At least 12, sir.
Okay. So this is 6, 7, 8, 9, 10, 11, 12. Okay. So gap is already complete. Okay, I'm going to zoom it a bit. Now I'm going to use the P diffusion actually.
P diffusion.
Not P diffusion actually. I'm going to use the polysilicon for gate. So it should be at the middle, exactly like the middle. So 3 lambda up, 3 lambda down, and the width should be 2 lambda at least. And now I'm going to use some contact here and here. So what I'm going to do, I'm going to click the P contact, this one. I'm going to bring it and I'm going to place it at the middle. P at the middle. And N at the middle. Okay. So this is for A. Our A is completed. Now I'm going to copy it for B. Why? Because our sizings all are same. 2, 2, 2, 2. The sizing of A is this, right? And the sizing of B is also this, same. So I can copy it. I can copy it, I can replicate it. I can make a copy of this, okay? If this is for A, this should be for B. Understand? So I'm going to copy the element. So gap should be 6. 1, 2, 3, 4, 5, 6. Okay? So this is for A, this is for B. So now, since our design is almost complete, so I'm going to check for error, no error. So what I'm going to do, I'm going to connect the, what is that? I'm going to connect them, but before that, here, see this. This is source, drain, 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 source, drain, source. Hello? Are you listening? Okay.
Yes, sir.
Okay. Now here, so which one is A, which one is B? It's completely your wish, okay? Let's say this one is our A, this one is our B, or this one is our A, this one is our B. Which one you will take as A? Left or right?
Left, sir.
Okay, left is our A. This is our A, so I'm going to write something. This is our A, okay? I'm going to write here. This is our B. So you will write this inside your head, not on the screen, remember? Okay, now this is our source, let's say. This is our drain. This is our source. This is our drain. Why? Can you call it this is a source? Of course you can, no problem. This is my wish. I always keep the source at the left and drain at the right, okay? If you want to call this is a drain, you can call it, okay? This is source, this is drain, source, drain, okay? Now I'm going to choose, oh, by the way, see, since source and source are connected, so this source and this source should be connected, and drain connected, so this drain and this drain should be what? Connected, right? See, the source connected and the drain connected, right? For PMOS. Understood? Okay. Now, then with their drain, A's drain is also connected. That means NMOS drain. Which one is A NMOS drain? This one, right? So this one must be connected with the PMOS drain. Can you see the PMOS drain and the NMOS drain? That means not all drain, only the A drain is connected, this one. So their PMOS drains and the NMOS A drain is connected. Okay, from there I will take my output. That means this is my output. Okay, then A source is connected with B drain. A source is this one, will be connected with the B drain. B drain is this one. Then B source has the ground. So here will be our ground. Understand? Where will be our VDD? our source will have our VDD. And here will be our VDD. Everyone understood? Okay. If you understand this, then we will proceed. If everyone understood?
Yes, sir.
Okay. Now we will proceed. I'm going to use metal 1 for connection. So source connection. This connection should be, or this should be at least 3 lambda, 3. If it is less than 3, you will get some error. Okay? And the gap between them, this gap, should be 4. The gap should be what? 4. That's why I have taken it like that. Or I could have took this like this. I could have taken this like this, right? But I didn't. Why? Because I want to keep a gap at least 4. That's why. Now source is completed. Oh, remember here you have to use the VDD. Okay. Source is completed. Now drain. For drain, I need to use metal 1. Remember, you have to give gap of 4. 1, 2, 3, 4. That means up to here. Okay, I can call it like this. Okay, at least 4. I have given 5. That's enough. So this is the drain. Now, this drain should be connected with this, right? So I'm going to connect the drain like this. Enough. So I'm going to erase this part. Remember, our output will come from here, right? Anywhere from here, anywhere. Maybe here, here, because all of them are metal. So anywhere from here, our output will come. Now, this source should be connected with this drain. So how to do that? Like this. Okay? Now, what if for some reason your connection becomes smaller? So you want to make it bigger. How can you do that? You can go to this slider, move or stress, click, click, make it bigger. Okay? No problem. Now, this is completed. I'm going to erase this. The source gone. Now, here you will have your VDD. Here you will have your source. Or you can give your ground, your ground actually. You can give your ground directly here, no problem. You can take a wire and you give the ground, or you can give your ground here directly. Okay, I'm going to give the ground. What is the ground? This is the ground. Okay, this is the ground. That means this is the ground actually. So I'm going to give the ground here. Why is the VDD? Here is the VDD, right? I'm going to give the VDD, that is this one. Here, 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 doesn't matter. Double click, it should be 5 volt. Okay, assigned. Now, I no longer need these. This is your O. O means output. I'm going to put the output anywhere here. But before that, we need to do one more important step. That is what? That is N well. Remember the N well? Remember the N well?
Yes, sir. Yes, sir.
Okay, I'm going to give the N well. This is the N well. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, that means everywhere it should be 6 lambda extra. Okay, 6, 6, 6, 6. So this is the N well. Now N well also need a VDD. So I'm going to click the VDD and I'm going to place it here. Double click, it should be 5. So 2 VDD. One will be your circuit VDD, another will be your N well VDD.
Sir.
Yeah.
The sizing of N well, where will be from? Is it from the body or from the diffusion? B diffusion or N diffusion?
Which one?
you size your annual size is 6.
Oh
So
yeah. Oh yes. Okay, wait.
6 from where?
Yeah, Abbas. Here your gap should be 6. Here your gap should be 6. Gap should be 6. Gap should be 6. And here your gap should be also 6. At least 6. Understand?
Yes, sir.
Okay. You can give more gap, no problem. But you cannot give less gap. Okay, let me show you something. Let me make some error. Now there is no error, right? DRC is rule checker. So I'm going to make it smaller. See, here there will be an error. See error, right? They said the extra n well surrounding diffusion is less than 6 lambda. That means it should be at least 6. So I'm going to make it 6. No problem, right? No problem now. Now, so here I told you the gap should be at least 6, right? So if I make it bigger, if I make it stressed, so now the gap is 5. You will see there will be an error. See? The lambda, 5 lambda between n well and diffusion is less than 6 lambda. So it should be at least 6 lambda. Understand?
Yes, sir.
Okay. So how can you understand and how can you learn? You make mistake and you check. Make mistake, check. Make mistake, check. Understood?
Yes, sir.
This is how you will learn. Okay, now here I'm going to put the input. This is our A, this is our B. So which one is our A? So this clock, add a clock. I'm going to click. I'm going to press it here. This is our A. Let's call it A. The voltage should be 5. See the size. See the timing. Timing is 0.09 and rise time is 0.01. Fall time, low time is, high time is 0.09 and fall time is 0.01. That means if they add, it is 0.1, 0.1. That means 0.1 high, 0.1 low, right? 0.1 high, 0.1 low, like that. Okay. I'm going to click and I'm going to make it B. So this should be B. See, the voltage already adjusted because we have already adjusted the previous voltage. That's why the voltage starts from 5. And the timing become double. Before it was 0.09. Now it is 0.190, right? So that was 0.1, 0.1. This time it will be 0.2, 0.2. That means double. Okay? Remember why double? Because if it is not double, we cannot see the other 2 stages. We'll only see 1, 1, 0, 0. Now the output will be taken from this line, right? So I'll take the output from here. So this is the output. I will click it and I will name it Y. Okay? So our circuit is complete. Is there any error? No error. So I'm going to make the simulation. Okay, this is very clumsy. This is very, what is that? What should I say? Very shrinked. I'm going to make it a bit zoom in. So I'm going to change the time scale from 5 nanosecond to 2 nanosecond. So now it will be what? It will be in much, what should I say? A wide output. Yes. Now see, here, this is your A, this is your B. Ignore the first one because there will be some problem at the first, what is that? The first pulse. There will be some problem at the first pulse always because we are actually designing manually. Manual design will have some problem at the first. But check out this. This is 0. This is 0. Your output is 1. This is 0. This is 1. Your output is 1. This is 1. This is 0. Your output is 1. This is 1. This is 1. Your output is 0. Right? Understood?
Yes, sir.
Your truth table is complete. Got my point?
0, 0, 1, 0, 1.
For 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. So that is the truth table that you have learned already from here. 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, right?
Yes,
understand?
Yes, sir.
So you got your truth table. That means your output is correct. Now what you have to do now, right now, what you have to do? you have to do the same design for NOR gate, NOR. And I'm going to check everyone's, what is that, drawing today. I'm going to check everyone's drawing today. Remember, when I will take the VLSI lab exam, this will be a very small exam, let's say 10 minutes or 20 minutes exam. But in that 20 minutes, you have to design one of these, and you have to design maybe full adder, half adder, and 4-bit adder, multiplex, something like that. So you have to practice for a very long time. If you practice, you can do it in 10 minutes. This design, you can make it within 2 minutes if you do not talk. Got my point? I can make this design within 1 minute if I do not talk. Understand? Hello?
Yes, sir.
So, design NOR. Do not see this. Maybe NOR is given. Maybe NOR is given. Yes, NOR is given. But you make the design from here. NOR is given, but you make the design from here. Okay?
Sir,
Okay, my dear?
yes, sir.
Okay, do it. Take 10 minutes and do it. I'm going to check everyone's work. I'm going to do the NOR gate now for you. You see here, I'm going to click new. I do not want it. No. See, okay, this one should be like this. Okay, now here I need what? See the sizing. This is 4. This is 4. This is 1. This is 1. Right? For A, you have a PMOS that is 4 and NMOS that is 1. 4 means what? Okay, by the way, 1 means 6 lambda. 4 means what?
Sure.
24.
24.
Right? 24 lambda. Okay. Understand. Now I need P diffusion, that is 24. This is 10. This is 20. 21, 22, 23, 24. This is 24. This is 1, 2, 3, 4. Like that. This big. Then I need NMOS. This is N. N should be 12. This is 6, 7, 8, 9, 10, 11, 12. From here, I'll start. This should be only 6, right? Because 4 and 1. Now I need P diffusion. This is P diffusion. So it should be at the middle. If you're not confident about, you can count. So 3 extra, no error. Now PMOS, for P type, I need what? I need these. For P, I need these.
স্যার এটা মধ্যে 24 আর 6 হলো আগের মধ্যে যে হচ্ছে গিয়ে 12 আর 12 ছিল মেবি আমি একটু ভেরি করছিলাম
হ্যাঁ 12 আর 12 ছিল কারণ হচ্ছে সাইজিং ছিল 2 2 2 2 দ্যাটস ওয়াই
2 2 yes.
This is N. Now I'm going to copy it. I'm going to copy this because our B, this is for A. Our B is also 4 and 1, right? Similar. So I'm going to copy it. Understand?
Yes, sir.
So for copy, always remember copy from the bottom. This is a tip. This is not a rule. This is a tip. Copy from bottom.
Okay.
Okay. Do not copy from the top. Copy from bottom. Then copy it. 1, 2, 3, 4, 5, 6. So remember, this is a tip. You will understand if when you copy a lot of things, you will understand why I have said copy from the bottom. Okay. Now this is for A. This is B. Now before going there, let's say this is your source, drain, source, drain, source, drain,
Drain.
source,
Drain.
drain. Now this one is source. This is drain.
Drain.
This is source,
Drain.
Here the drains are connected.
Drain connected. Yes, sir.
Source are connected.
Source is connected.
And there, that means
This
A,
drain and drain.
see, A drain is connected with B source.
B source.
B drain is connected with AB drain.
Drain.
AB sources are connected. So this is the rule. That means A source will be connected with VDD, right? AD and B source will be connected like that. Then this one drain will be connected. Source will be connected.
Connected.
DD will be connected because that drain and this drain will be connected.
Connected.
That's it. Your circuit is complete. So let's make it.
So metal 1.
Metal 1. This one will be connected.
Okay.
This one will be connected.
This one and this one.
Take this. Do not give a. So this is 1, 2, 3, 4. Yeah, 4 gap. So here we have to make it a bit bigger. Otherwise, it will give you an error because it is 2. That's why. Now this one will be connected. No. Metal 1.
Metal 1. This go there. Then go there.
Wait a minute. I have a phone call. I need to attend that.
Okay, sir. কি করলাম
Now we have already connected all of these. So this is the connection. Now what I'm going to do, I'm going to erase this thing. This thing is no longer required. That means these no longer required. So here I will connect my VDD. Here I will connect my output, because the connection between PMOS and NMOS, that is our output point. And here we will connect our ground. See, the source is the ground, right?
Yes, sir.
Okay. Now this is no longer required. Okay, this is the VDD. VDD will be here. Double click. This should be 5 volt. This is the ground. No, this is the output. Output should be from here, right? This
Yes,
should be Y. What is the ground? Here is the ground. Ground should be here. Anywhere here or here or here. Anywhere, no problem. This is the ground. Now we have missed one more thing, that is N well, right?
Yes, sir.
So we'll put the N well. So 1, 2, 3, 4, 5, 6. So this is 1, 2, 3, 4, 5, 6. This is how I do it. You can do it in another way. I need to give one VDD here as well. Anywhere. Let's say give here. Double click, it should be 5. Now I need to give the inputs. Remember, to give the input, you need to keep some spaces empty. Okay? So this is the input. So here I'm going to give A. This was their A, right?
Yes, sir.
A. The voltage should be 5 volt.
5 volt.
And do not touch the time. If you want to touch the time, you have to be very sure that you know it. You know what you have to know what you are doing. Okay? But if you do not know, if you're not sure, keep it like this. Here I'm going to give B. The voltage is already adjusted, time is adjusted. Now this so we are done actually. So if we run it, you will see this is your graph. So here, ignore the first one. For the second one, these. So what is happening here? For 1, 1, your output is 0.
0.
For 0, 0,
0,
your output is 1. For 1, 0, your output is 0. For 0, 1, your output is 0. So this is the NOR gate. For 0, 0, your output is 1. Okay?
Yes, sir.
So this is your output. Understand, everyone?
Yes, sir.
Okay, I believe you can do it. Now I'm going to go for the next lab. Okay, your practice should be 3 input NAND gate and 3 input NOR gate. Practice this thing at your home. I might give you question from here as well. Okay? Now the third lab, that means lab number 6, layout design of a custom logic expression. Y is equal to AB plus CD. Y is equal to AB plus CD. This will be our custom logic expression. We will be designing this by using what? Using mask layout. Okay, reference, we will be designing the mask layout. So convert these into what? Into a logic based, or I should say transistor based circuit. NMOS, PMOS. Then after that, you should do the sizing. So we consider 2:1 here. That's why 4, 4, 4, 4, 2, 2, 2, 2. Okay? So we will do that now. And drain and source, they are actually indicated here. So you have to do not have to worry. So we'll make it, right?
Yes, sir.
So I'm going to do it by myself. You have to do it at your home. And by watching the video, obviously. The video is, okay, recording. So I'm going to click new. Okay. So I need, see everyone, this is a pretty simple one, because your A is 4 and A is 2, 4, 2. B is also 4, 2. C is also 4, 2. D is also 4, 2. That means you can actually copy, right? You can copy. If they are different, you cannot copy. But since they are same, you can copy. Okay?
Yes, sir.
Okay. So I need P diffusion. Since it is 4, so it should be 24, right? So this is 20, 21, 22, 23, 24, 11, 12, 13, 14. Okay, so this wide width is what? 24. The length is obviously 14. Come down. End diffusion. End diffusion should be at least what?